Hello, my name is Marquis McMillan. I'm an undergraduate at Penn State University, and today I'll be talking about my summer project dealing with superconducting qubits using IBM's quantum computer remotely. Quantum computers use quantum bits that can be in a superposition of states, whereas classical computers use binary bits in a definite state. Here on the left, we have a classical bit that has a definite state of 0 or 1, and on the right, we have the block sphere model of the qubit where a state vector psi can represent a superposition of states. The qubit is a two-level system analogous to spin, and the use of qubits are theorized to accurately model quantum systems. Since a quantum computer is a sensitive quantum system, the qubits are cooled to temperatures near 10 millikelvin by using a helium-3, helium-4 dilution fridge. To transform the state of the qubit, we supply the qubit with the energy needed to excite to the next state, or we relax the qubit to the ground state. The energy to excite or relax the qubit is associated with the energy difference between the two states. The energy difference between the 0 and 1 states of the qubit can be represented as a frequency, and this frequency is named the fundamental frequency. In quantum computing, the idea is to encode information through transforming qubits by using this frequency. Therefore, it's important to accurately measure this frequency. In our case, we study the transmon, a type of superconducting qubit made from a superconducting circuit. An LC circuit is the basis of a superconducting qubit. So essentially, we can quantize the circuit Hamiltonian by the number of oscillating Cooper pairs within the circuit. However, the energy spacing between each level must be unique, otherwise the excitation of higher order states may occur. So what we'd like is a nonlinear energy increase in the Hamiltonian. To provide a nonlinear element to our superconducting circuit, a Josephson junction is implemented. A Josephson junction consists of two superconducting plates with an insulating barrier in between. This setup induces the Josephson effect where Cooper pairs tunnel through the insulating barrier while maintaining superconductivity within the insulating barrier. The nonlinear inductance in the Josephson junction is the key to providing nonlinearity in the Hamiltonian. The diagram on the left is the Josephson junction used in our transmon at IBM, and it consists of two aluminum fingers with an aluminum oxide lighter between. The transmon is derived from the Cooper pair box, a type of charged qubit. The Cooper pair box can be represented by the diagram at the top left, and the Hamiltonian can be determined by the Josephson and charging energy coefficients EJ and EC, where Ng is the excess charge in the circuit and depends on the gate voltage and gate capacitance. The transmon is when EJ over EC is equal to 50. To reach this, the junction is shunted by a large superconducting plate capacitor sufficiently decreasing the EC coefficient. In our case, the transmon uses niobium. And like I said before, the temperature of the system is around 10 millikelvin, and this is to suppress thermal fluctuations in a circuit that typically operates at about 5 gigahertz. It is known that the excess charge fluctuates due to charge noise in the voltage source. So if we look at the eigenvalues for different states of the Cooper pair box and the charge basis, we see that the eigenvalue fluctuates with different values of excess charge. In turn, this would enable miscalculations in the fundamental frequency. So in this case, we would want to operate at half integers of the excess charge because there's a minimum slope between the energy levels and a gap exists. Entering the transmon regime, we can see that every excess charge value can be operable with minimal error in the computation of the fundamental frequency. Additionally, we can see that the transmon remains anharmonic, meaning that the spacing between the energy levels is still distinct. The transmon is set up on the scale of microwave pulses, so by coupling the transmon to a resonator, we are able to measure the transmission of the microwave through the resonator to probe the state of the qubit, since the resonator's resonance frequency is sensitive to the state of the qubit. This is very similar to what we have at the top left, atomic QED, and to where we have two mirrors inducing a cavity in the atom. However, on the right, we have a circuit where we have two cuts between the middle coaxial tube, creating a cavity. We measured the absorbance at different drive parameters and found the qubit frequency at maximum absorbance. To determine the drive parameter that promotes the qubit to the first excited state, we performed a Rabi pulse experiment where we varied the drive parameters and compiled a list of absorbance at the suspected fundamental frequency. As seen, we detected two peaks in our spectroscopy data for each different drive parameter. Based on literature, the suspected frequency is below 5 GHz. However, we have a peak greater than 5 GHz, so we consider this peak unknown. To test each frequency, we perform a Rabi pulse experiment to test Rabi oscillations. On the left, we performed a Rabi pulse experiment to test the suspected frequency, and on the right, we do the same with the unknown frequency. As we can see, there are Rabi oscillations in the suspected frequency, but not the unknown frequency. Therefore, 4.975 GHz is our fundamental frequency. And we can define a 180-degree rotation about the block sphere as the period divided by 2, which is 0.24. So we can conclude and define a pi pulse at an amplitude of 0.24 and frequency of 4.975 GHz. This method for finding the fundamental frequency of a qubit is accessible and accurate and paves the way for remote experimental calibrations. Thank you.